Let's imagine a pipe with water flowing through it. The pipe has a change in diameter and elevation. As the water moves from point 1 to point 2, three things change: the pressure, the speed of the flow, and the height of the pipe. Because energy is conserved, any gain in one of these must come from a loss in one or both of the others. At point 1, pressure P1 pushes the water forward into the next section of pipe. At point 2, pressure P2 pushes back against the flow. So the net pressure force acting on the fluid is shown by the following equation: P1 minus P2. This difference in pressure is what we call the static pressure term in the Bernoulli's equation. The work done by this pressure difference supplies energy to the fluid. The pipe widens, the velocity changes according to the continuity equation. The kinetic energy per unit volume of the fluid is denoted by the following part of Bernoulli's equation: a half rho v squared. So the change in kinetic energy from point 1 to point 2 is shown like this. Because point 2 is higher than point 1, the fluid must gain gravitational potential energy. Potential energy per unit volume is shown by the following equation: rho gh. So the change in potential energy is shown here: rho g multiplied by the difference between h2 and h1. Now we apply the energy balance. Pressure work equals change in kinetic energy plus change in potential energy. So P1 minus P2 equals half rho V2 squared minus a half rho V1 squared plus rho G multiplied by the difference between H2 and H1. Rearranging to collect terms at each point, P1 plus half rho V1 squared plus rho G H1 equals P2 plus half rho V2 squared plus rho G H2. And since this applies between any 2 points along a streamline, we write the general form: P plus a half rho V squared plus rho G H